when you have followed my channel, you will surely know that I was busy with a, say, primitive oscilloscope and a sawtooth generator. It was made in an earlier schematic with a field effect transistor. It worked very nice. But in a certain way I could not get that circuit completely under control. Like a piece of soap, it acted a little bit like a piece of soap. I don't say that it was not okay. It worked very nice, but it was in a certain way limited in its frequency band, and then I mean that you had to use two different setups with potentiometers to get to the complete frequency band. Anyway, I will give the link in the description of this video anyway. So here is that field effect transistor circuit. Here it is, and you can see that I tried a lot with two different potentiometers to make it work, and it works very nice. It works up to approximately 5 kilocycles, but the issue was that when I switched here, when I switched the frequency back here, when I switched it back, sometimes the oscillator did not want to start till, say, switch back to a certain capacitor, say 10 nanofarad or so, or 47 nanofarad. Anyway, so I searched further and further. Of course, I met the beautiful 555 chip, and this is, say, a circuit of a linear ramp oscillator. That is what it is called, but I made it and it is far from linear, and it simply doesn't work. And you can also find this circuit on the World Wide Web, where they are talking on certain websites about exactly the same circuit. Elaborated, all calculations around it, but when you make it, you will see, perhaps, and I'm almost sure, that it doesn't work in the way that this linear data book, by the way, a brilliant book, no criticism on that, tells that it has to work. So this is what you had to see according to the linear data book, but I did not see anything of that. So I went on and on making my own circuit, and here is a circuit that surely works with that 555 chip used as a sawtooth generator. When you do experiments with that chip, you see often that you find a square wave out, and when you look here to all the graphics, say all the, say this, for instance, this here, this is, say, the relation between the capacitance and the resistance and the frequency, etc., etc. They always talk about, say, how to get a square wave out, etc. Well, that was of course not my aim. And when you do these experiments, you will surely find a square wave out, but not a sawtooth wave out, though that's very important to tell. Parallel to the capacitor here, there is a sawtooth wave, and I've amplified it. and found out all the components to make it work. Anyway, so the schematic. Of course, that second transistor acts as a kind of amplifier, but it also has to amplify that in a kind of linear way. So the waveform here that's present here must be amplified in a linear way, and that's the reason why you see here all these potentiometers, and they show here the bias via that 250 kilo ohm potentiometer, and here we set the waveform. Very, very important, and of course the bias and the waveform are working together. The settings of the positions of the potentiometers are critical. Pin connections of the BD139. Here is the chip, the 555 chip here, and it works between 30 Hertz and 43 kilohertz. I had not expected that, but anyway. Now we are on 60 Hertz. This is the waveform. Of course, the linearity here is not perfect. I tested all kinds of circuits, but this 555 chip worked finally at its best. And I will turn now here the frequency potentiometer. That's here. There is a fine frequency potentiometer here, and a coarse frequency, that's here. So let's tune the coarse potentiometer, see what happens. So well, this is the waveform correction potentiometer. That's the first important thing to tell. Here is the frequency potentiometer. So let's see, we are now on 59 Hertz. We go to a higher or lower frequency. Let's see. So even on this low frequency, 29 Hertz, there is a good, quite good sawtooth wave, ramp wave. Well, so higher and higher, and of course you can focus on 50 Hertz or 60 Hertz, etc., etc. This is of course not very linear, but anyway, I think it is quite good for hobby purposes, etc., etc. So now we are going to the highest frequency that this sawtooth generator can bring. Of course, not the real highest frequency. The real highest frequency is in the order of 50 kilocycles. But anyway, I disconnect now the timing capacitor here, and I disconnect now here this 0.47 capacitor that is here in a row, in the row. This is the timer capacitor, of course, in combination with the potentiometer. This charges the cap. So this is the R, and this is the C, and this is the RC time. That's classical in electronics, but anyway, here we have the highest frequency, 40 kilohertz, and it is still quite good. 40 kilohertz here the waveform, quite good. And let's turn the frequency potmeter. and I have also figured out both the fine frequency potentiometer, the fine frequency knob, and the coarse frequency knob. So now it's 90 kilohertz. Turn that potmeter again. We are on 40 kilohertz. That is surely a very good result. So 40 kilohertz. And let me tune now the fine potentiometer. That is this one. It is 100K and it is here. So I think you will not find this circuit on the World Wide Web. Perhaps you will find it somewhere, but it is invented by me and it works very, very nice and properly. So let's tune here the fine tuning. You can see a small movement here, but let's look at the frequency counter. 46 kilohertz, 38 kilohertz. So that gives it in my opinion a proper alignment. Thanks for watching. It was quite short, but anyway. Pen over somewhat. This is of course the 7812 voltage regulator, so that we have here a fixed voltage. That's important always when you make, say, a measuring circuit like this. You need a stabilized voltage. The diode here has not a specific cause, but anyway, it's there. And well, here of course you can use here a rotary switch with all kinds of different capacitors, and with that rotary switch you can switch to different frequency bands, combined with the fine tuning and the coarse tuning of the frequency. Thanks again. This is of course looks very sloppy, but it was all well thought out.